Well, hello everyone, and thank you for joining us today. I think we'll get started. We know that you're very busy, and we really appreciate you choosing to spend the next 45 or so minutes with us. Today's webinar is the second part in a series of 5. The title for the series is Using Graph Algorithms for Advanced Analytics. This one focuses on centrality algorithms. We hope you enjoy this presentation, and we hope you find it informative. Next slide. Before we begin our workshop, here are some housekeeping items. Although your phones are muted, we do want to hear from you. Please submit your questions at any time using the Q&A tab in the menu box as shown here. This webinar is being recorded and will be uploaded to our website shortly at www.tigergraph.com/webinars and events. And also we'll email you the URL to the archived version of the webinar very shortly after it concludes. Last but not least, if you experience any technical issues, please contact Victor or myself, and we'll do our best to resolve the issues in a timely manner. Next. At this point, I'm very pleased to introduce my esteemed colleague, Victor Lee, who is Head of Product Strategy here at TigerGraph. Victor has been with the company for 4 years and 9 months, and he has a BS in Electrical Engineering and Computer Science from UC Berkeley, and a Master's in Electrical Engineering from Stanford, and a PhD in Computer Science from Kent State University. So needless to say, he's a very capable individual, and Victor is joining us from Cleveland, the Cleveland, Ohio area today. And with that, I'm happy to turn the microphone to you, Victor, to get things rolling.
Thank you, David. Thank you for that introduction. And sorry, oops, I'm flipping around slides there. Okay, so as he said, this is part 2 in our webinar series on graph algorithms and advanced analytics. And we're going to be doing our demo today using TigerGraph running on TigerGraph Cloud. So it's really easy to get started there. If you haven't tried it out yet, we'd encourage you to follow up. You'll be able to replicate the demos that I do today using a free account on TigerGraph Cloud. So this outline for today is we're going to recap some things from part 1, call it the what and why of graph algorithms. And then we're going to jump into centrality algorithms. And we're going to look at about 4 different ones. And the whole point is to understand what makes them different. Why are they considered centrality algorithms? But why is each one a little bit unique? And then we will demonstrate them using the same sample graph that we used last time, the network of scheduled air flights around the world. So graph algorithms are functions for measuring characteristics of either entire graphs or some vertices or some relationships. Now, people don't normally think of algorithms as functions, but in this case, I want to emphasize the fact that, okay, we have a data set, the graph. You specify some inputs, possibly in addition to the whole graph. And then there's a particular thing that you want to know about the graph, and that's the function. And then it outputs some things. So in that sense, it's like a mathematical or a computational function. You provide some inputs, you get an output. And when you think about it that way, then algorithms are like tools. And there are hundreds of different graph algorithms that have been established over the decades of computer science and graph theory. And there are families of algorithms. Some are very similar to each other, yet they have their differences. And so there are different types of tools. And then even though there are hammers, there are wrenches, there are screwdrivers, there are lots of different types of screwdrivers, different sizes and weights and different tips, etc. So in that sense, to become a good practitioner, you want to learn which ones to use in different cases. And the other thing is, and that way we're thinking of them as tools, But because they're functions, they're actually also building blocks because you can put them together to assemble something greater. And so that's the sort of perspective that we have on them. And again, we used this as a motivational example last time. So what are some of the questions you can answer with graphs? And we're going to focus on those two on the top this time. Given a graph, which entity is most centrally located? And where are some of the use cases for delivery logistics, or when you're thinking about greater visibility, and that can be actual eyesight visibility or just exposure in terms of, you know, marketing. So, and some of the algorithms we're going to look at today are Closeness Centrality and Betweenness Centrality. On the other side, we say, how much influence does this entity exert over others, where the means of communication are represented by the graph. And then you have a much more of a marketing spin here. Or you could also think about possibly some viral spread. You know, if a virus infects a computer system, how might it spread? Which are the most vulnerable locations? So the central locations are the most vulnerable, so you want to make sure you have the greatest protection there. And then we'll look at the PageRank today. And so we actually classify both of those as certain types of centrality. And you see there are other types of questions, and we'll be covering some of those other questions in the coming weeks. We have a graph algorithm library in our language, GSQL. It's written in GSQL, so it's fairly high level, and the execution is parallelized. And the algorithms are open source, which means that you can modify the algorithms. I'm going to be demonstrating that today to show how we can tweak the algorithms, what's available in the library, to perform the function that we want. And there's also lots of documentation available for them. And this is sort of a checklist of some of the features. They do run in the database, so you don't have to export the data. And then you can actually update the database with the results of your algorithm. And as I said, you can modify them. The GSQL language is Turing complete, which means you really can do anything that you want to do. And it's designed to execute with massively parallel processing. So to review what we talked about last time we gave the general introduction to graph algorithms and their uses. And then we focused on path algorithms. I'm not going to repeat the information about path algorithms. You can go watch Graph Gurus number 26 if you'd like to see that. But these are some 4 basic points. So they answer fundamental questions about your connected data. They can be organized in a library, and if so, then you have an analytics toolkit. You can also think of them as building blocks for answering more complex business questions. And then when you learn the ins and outs of different algorithms, you'll find out not only do they answer different questions, not only do they have different requirements for what type of data they work on, some are faster or slower than others. And they all exist. You can run all of them on a small enough graph, but when you start to get to massive data, some are going to become more practical than others, some less practical, and that's useful to keep in mind. And those are fundamental limits. They fundamental in people write mathematical proofs to prove that it's impossible to run this algorithm any faster. You could get faster hardware, but as far as the number of steps involved to execute that algorithm, there's a theoretical limit, and that's just the way it is. So again, and then the whole point of this series is to help you learn enough about these different algorithms so you know which ones to use for different cases. So we introduced these different types, and this more or less represents the sequence that we're going to go in. We didn't talk about search in particular. That's really just talking about how do you traverse the graph, because once you traverse the whole graph, you'll eventually find what you're looking for. If you cover the whole graph, you'll find it. But then you apply those fundamentals of search to pathfinding. And this week, we're going to look at centrality and ranking. And that's where, if you look at the set of scores for centrality, which ones are the most central. And we'll actually see that this is building on top of shortest path algorithms. And that's one reason why we did shortest path first and then did centrality. So here's the basic question. When you have a graph, a network, which node is the most centrally located? And that location is not necessarily physical. And it's useful to remember that the way that I've depicted this graph, I could have stretched things around. I could have oriented it differently. I could have arranged it so that A looks like it's in the center. These are not physical locations here. I'm just trying to find some convenient way so that I don't have lines crossing and things are nicely spread out. These are not physical locations. So what do we mean by centrally? It usually has to do with how do you get from one vertex to another following the edges. So the edges might represent road segments if there's a physical analogy. They might represent cables in some sort of communication network. It could mean who knows whom. So if this is a social network, I know you, and therefore, if you want to pass on information, you're going to do it through your contacts. And so that may be, if you're analyzing viral messaging, who is if you want information to spread, and if the graph represents how things spread, who would be the person that you would want to first tell so it has the greatest reach? So really what we're looking at is the abstract concept of travel or traversal. It could be a physical good that's moving, or it could be just information, electrons, or ideas that are moving. So when we're talking about centrality, there's this abstract concept of traversal or travel. So again, here are some real world examples. Could be thinking about a distribution network. Where should I put my distribution center or my warehouse so that my trucks can, on average, travel the shortest distance and have the fastest delivery times to their destinations? A related question is, where should I put my Starbucks or my gas station so that people who are going from place to place are most likely to pass by my business? Now that's considered a good, where it's a good corner for putting my business, where I'm going to get the most cross traffic. Or if you're looking at social dynamics, again, which entity in the group has the most influence? And then we have to look at how do we strictly define influence? You can write an algorithm if you define the terms of what exactly you're looking for. So each of these have a slightly different definition of what you're looking for, maybe a different definition of the rules of motion. How are you allowed to move? So look at this case. Here's a centrality for a distribution center. So if these are the possible roads, this might say, this is the location. Now this actual graph, this actual picture is not showing the roads, it's showing a routing. And this is actually a more complex question. This is looking at, if I want to say that this vehicle 1 is going to make 4 deliveries, what's the most efficient routing? And why did I bundle them with vehicle 1 and not with vehicle 2? So that's a more complex question, which we might get into in a future webinar. But if you think of this as just showing the roads, and the question here is, if I might need to make a delivery to any of these places, where's the best place to put my distribution center so that it's not too far to get to any of those places? Airline hubs, that's another example. Where do you put your airport so that the flights to and from are the shortest? And now when an airline, so we've got Denver here and Chicago, and this looks like, actually that looks like New York, and Washington. This looks like United Airlines, except there's nothing on the West Coast for some reason. So they have the existing airports, and they decide which airport should I designate as a hub. And so again, so that the distances that their passengers and their planes have to travel is the most convenient, the least distance. When we think about influence, So here's an example that we often refer to. We often like to think about the healthcare industry. It's something that impacts all of us directly. And it's also, there's a lot of important business questions here. So the importance of finding who are the most influential medical providers or prescribers. And you can subdivide that into a particular region for a given specialty. But why would you want to know this? If you're trying to understand what impact the providers are having on the patient community, and it could be who is just having the most business, who has the most patients. That's a simple question. But we suspect there's more of a viral effect or referral effect. So in this case, if you're looking at specialists, people often start with a more general practitioner before going to the specialist. So why did they end up with that specialist? Did they end up with that specialist through referrals? And if it's through referrals, and there are other types of businesses. Once you understand the concept of referral, you could think of other businesses where a lot of word of mouth is used. And then the most influential person is the person who received the most referrals. And then it's not just a count, but it's also what was the impact, the person who is making the referral, how much influence do they have? So it becomes this multi-layered or recursive question. It's also been used when you're thinking about, again, selling. Who in a market has the most pricing power, where if one company wants to make a change, will it be sort of accepted and embraced by the market, and where everybody reacts to it in a way to accept that price change? Or will they be sort of forced to scale back because the network is kind of rejecting their change? So that's almost a game theory question. So there are a lot of different algorithms you could have here. If you go on everybody's favorite website, Wikipedia, whether you think it's a good source of information or not, for computer science information, it's actually often very good because CS people will monitor it rigorously. So you'll see a list of 8 or 10 different centrality algorithms. I've listed some of the most common ones here, some that are very common and some that are less common. And we're going to cover about 4 of these today. Degree is very simple. Degree, if you might know, is just counting how many edges connect to a node. And so it's just a simple count of the edges that connect. And it's like, obviously, that's one simple measure of centrality. How many direct connections do you have? And then they start to get closer or more complicated. We're going to look at closeness, where what you're doing is, if you ignore the scaling factor, it's 1 over the sum of these, and D here is distance. So it's distance between the vertex in question and all the other vertices. So again, this is where we talked about the average distance. So we want to minimize the average or total, because total is sort of scales with average, right? So minimize the total distance to all your neighbors. And it's 1 over because we want a minimum rather than a maximum. And I'm not, my point isn't to explain all the mathematics here. If you're, proficient in reading these type of equations, this may give you some greater intuition. But my point here was really to show you that there are many ways to define what we mean by centrality. There's a fairly simple English description of each of these, the inverse of the sum of shortest path distances. So I said we're building on shortest path. Harmonic kind of twist this, it's the sum of the inverses instead of the inverse of the sums. Betweenness is which node sits along the most shortest paths. So if you consider all the shortest paths from any vertex to any other vertex, so it's like n squared for the number of paths to consider, which node shows up as somewhere on there the most often. And you can see the relationship to that question we talked about earlier of like, where do I put my Starbucks so it sees the most cross traffic? Hey, maybe I should use Betweenness. So let's start to look at a little toy example. How would you compute the average distance from a vertex to every other vertex? And remember, closeness is like the inverse of distance. If something is distant, it is not far. It's not close. So we've got this graph. I've highlighted F, and we're gonna calculate the distance to every other vertex. So you see, these are its 3 immediate neighbors. So there's a distance of 1 to those. And then to the others, there's a distance of 2. So it's a small, small graph. Maximum distance from F is 2. And then let's just add these up. So this is an unweighted graph. We're just counting the hops. Each edge counts as just 1 unit. So if I sum up, and the order I'm going in is A, B, C, D, E. So A is 2, B is 2, etc. And I divide by 7 because there are 7 neighbors, or 7 other graphs, 7 other nodes in the graph other than F. So total distance was 11 divided by 7. I take the inverse of that to get the closeness. So the closeness centrality is 0.636. If I look at A instead, it has 3 immediate neighbors, B, C, D. E and F, you can see, are 2 steps away, and G and H are 3 steps away. So the sum is 1, 1, 1, 2, 2, 3, 3, which adds up to 13. So 13 over 7. The inverse of that is 0.538. So we see that F has a higher centrality score than A. And you could probably convince yourself that F has the highest, or at least it's tied for the highest. If you pick anything else, I think there's going to be at least, actually B. Well, the question is, okay, there are other vertices you can pick where nothing is more than 2 hops away. But then there becomes a question, how many are 1 hop away and how many are 2 hops away? So if I pick B, I see it has 2 immediate neighbors. So I already know it's not going to do as well, because with F, I had 3 immediate neighbors. B, I only have 2. So even though it looks like every other vertex is no more than a distance of 2, but because I started off with only 2 cases with a distance of 1, B is not as good as F. Oops. Now, what if I had a weighted edges? Remember last week we showed this graph also with weights. Then I can't just count hops. Then I do have to use a proper shortest path algorithm, such as Dijkstra's. And so you run Dijkstra's, but you pay attention to that total. So it's just adding a little bit of more work to what we would normally do with a Dijkstra's shortest path algorithm. It has the same, it's considered the same execution time because you're not really doing any extra steps. You're just doing a little bit more with each step. Now, what if you have a directed graph where you can only travel A to B, A to B, but not the other direction, not B to A. So if it turns out, say there's actually no way to get from B to A because you run into so-called one-way streets and there's no way to loop back, then the distance is 0. So if there's distance is infinite. I'm having a little trouble with saying the word that's in my mind today. So if one of these, just any one of these numbers is infinite, the total is going to be infinite, and then the closeness is going to be 0. So does that make sense? If there's just one pair of nodes that's unreachable, do we like that answer? Well, in some sense, what's that saying? It's rejecting that answer. So if there's just one case, if I can't get from B to A, but I could get from B to everybody else, well, at least I can say B is not going to be my best answer if I do want to consider every possible destination. So You could debate whether or not 0 is the right answer, but I would say if you're looking for the best answer where every destination matters, it's true that you should rule that out as a best answer. So let's look at Betweenness Centrality now. So this again it's using the criteria which vertex shows up the most often along a shortest path. And you can sort of see this is instantly harder to do in your head, even with this graph that only has 8 vertices, because now I have to think about all the shortest paths. How many are there? Well, if you have an undirected graph, simple formula, n is 8. There are 8 vertices. 8 times 7 divided by 2, because if we're undirected, A to B is the same as B to A. But if you do say direction matters, then it's just 8 divided by 7, because from each vertex, so there are 8 different cases of from, and there's 7 cases of to. So from 8 to 7, 56. 56 possibilities. I can't do that in my head. So that tells you that this algorithm is considered computationally more complex. Now, this is certainly small enough. Sure, a computer can handle that, no problem. But I just offhand, I don't know what the answer is. I kind of guess it's somewhere in this area, but we could check. PageRank. Here, I'm actually representing slides that I used probably over a year ago now in Graph Gurus 5, where we talked just about PageRank. But so now we're comparing PageRank to these other centrality measures, closeness and betweenness. So here, when PageRank was first developed by Larry Page and Sergey Brin, who ended up founding Google, they wanted to take a web page, and so each page is considered a node, and say, which is the most authoritative page? And the reason why is, okay, in the we're talking early days of the web, they had, oh, there's like maybe 10,000 web pages, oh, 100,000, a million, now there might be trillions now. So you can run a search. You can say, okay, show me all the pages that talk about dogs. There might be hundreds of pages. Which one do you put at the top of the list? Because no user is going to read through the hundreds of thousands of matches. Which one do you put at the top? So this is a ranking problem. And they came up with this idea of authority. So which pages are the most authoritative? And the concept they came up with is, because it's the web, the whole point of the web is to have one page point to another. Who has the most pages pointing to it? That makes you more authoritative. And here's the concept. There are actually 2 principles which work together. So if you think of it as people referring people, remember the healthcare providers. These could be healthcare providers. They could be web pages. This has 2 entities pointing to it. This one has 5 entities pointing to it. So that means B should have a higher score than A. Now, this is just using counts. This one is using the authority of the referrers. So here, C1 and C2 have just base level authority. Here, D1 and D2 have higher authority than C1 or C2. Therefore, when they make a recommendation, it's worth more. So even though the count is the same, but the fundamental authority ranking of D is higher, so that passes on from D1, D2 to D. So here, the count matters. Here, the authority of your referrers affect your authority. So that's a recursive definition. So that is basically, that gives us what we need to do to start to make a formulation for PageRank. So 2 principles, we encode them. The PageRank of V, which is the authority of V, is the sum of its referrals or referral strengths. Then what is the referral strength? The referral strength is, it's the authority of, this should be, sorry, I didn't write that quite right. Let me see if I can edit the slide right on the fly. Oh, it's a referral, I'm sorry. It's a referral by X, but I didn't say to whom. So this is correct. So when X makes a referral, it takes its own authority strength, But then because it's spreading it out among multiple destinations, it gives a fraction of its authority to each destination. And that's why we're looking at out degree. So you think of this person, he has 4 possible destinations he can walk to. Each of his authority, or rather likelihood of traveling there, is divided 4 ways equally. We just divide it equally because we don't have any other basis for making a decision. So then you, in this other step, you sum the weight of each of those referrals. And this can also be thought of the so-called random network surfer. You do a random walk on the graph. Start anywhere. And again, when you get to a node, pick any of the possible destinations, and then keep doing that, keeping that step at a time forever. And then your PageRank turns out to be, it's the fraction of time that you end up spending on a particular node. So the PageRank of V is the fraction of time you spend at V. This is really designed for directed graphs because that referral is a directed relationship. If you try to make it with undirected graphs, the concept really doesn't work, because then authority, are you authority because people look to you, or because you have a lot of outlinks? It's the difference between inlinks versus outlinks. Are you an authority or a hub? So it really is for directed graphs. I think for time, I'm going to skip over these slides. Again, these were presented previously in Graph Gurus 5. But I do want to talk about teleportation and then personalized PageRank, and then we'll go to our examples. So what I've talked about, the random walk, is great. Turns out there's sort of 2 technical problems. And so to fix the problems, we throw in an extra process. It's called teleportation. And this says, in addition to walking the graph, there's a possibility that you can just instantly jump from one vertex to excuse me, from one vertex to another. And then the overall probability that you observe the graph and follow the edges is called the damping factor. And the probability that you teleport is the inverse. So 85% probability that you follow the edges, 15% that you teleport and pick a destination at random. You could go to any of these. So V0, you could teleport to, if there are 5 others, there's a 15% probability that you will teleport. And since there are 5 possible, actually 6, you consider teleporting and sort of staying where you are. So there are actually 6 possibilities. So then divide 15 by 6, there's a 2.5% probability of teleporting to any of these. This solves 2 problems. From just the pure mathematics, this doesn't, the PageRank process that we talked about doesn't work well if there are either so-called source nodes or sink nodes where one has no in edges and the other has no out edges. They tend to either absorb all the probability if there are no out edges, right? Things go in, they don't come out. And then when we're applying this to the original web surfing problem, which web page is the most authoritative, people don't always, you don't just follow hyperlinks. You sometimes just go directly to a page you want to go to. So it both explained real behavior and it solved sort of a computational problem with the pure PageRank. The so-called pure PageRank is actually something called eigenvector centrality. When you add in teleportation, then it becomes what we know today as PageRank. This is the GSQL formulation for it. And again, in the interest of time, I'm not going to go over this in a great lot of detail. Again, it was presented in Graph Gurus 5 because I want to get to actually the demo. And I'm just going to mention personalized PageRank very briefly, also known as random walk with restart. So take PageRank, but make a few modifications. So instead of just starting at any vertex, you start at certain selected home vertices. You could pick one, you could pick a dozen, whatever. These are your so-called preferred vertices. And again, when you initialize, you start there. You don't start anywhere else. And then when you teleport, you don't teleport to just any vertex. You teleport to one of the home vertices. And that's what this restart means in this name, random walk of restart. You jump back to a home vertex. And when you think about it, the random walk is you're starting here, and it makes it less likely that you're going to wander far from there. So all your travels, they're going to tend to congregate near where you start. There's always some possibility that you could go very far without teleporting back home. It's just the farther you go, the higher the probability that you will eventually teleport. So it's rare to get far from home. All right, let's jump into the demo. So again, I'm looking at Airline network, and I'm just gonna go right into it so this is my TigerGraph Cloud dashboard. I've set one up already, one machine called Graph Algorithms 2. And I made a little bit of change from the data set that I used last time, or the schema. Last time I had this undirected edge. So airport flies, there's a connection between two airports, but this was undirected. And if you remember PageRank, I want directed edges. So this is actually identical in its properties, except that it's directed. It also has a so-called reverse edge. So if you look at the properties, it's called flight 2. So the name implies it's going somewhere. I clicked the directed checkbox. I also have a reverse edge in case I want to talk about looking back to where you came from. We had the miles attribute. I also added another one, which I haven't used yet, but I thought I might want to know how many flights are available between these two cities. So it's not just that there is a flight, but how many flights. So that's how we modified the schema. We now have two different types of edges. I also have two different sets of data. This is the data that comes from the openflights.org website. And I wanted also a small demo graph. So I added some of my own data, and that's why it's showing two sets of connections. So again, you see we still have this about almost 8,000 vertices. They're now flights 2 and the reverse flights 2. So for every forward edge, there's also a reverse edge. This is showing that sample graph that we actually had in the slides. And you can see the distances there. But I want to get to what we're going to do here is I'm going to go to our graph algorithm library and show some minor modifications we're going to make so that we can do closeness centrality, betweenness centrality, and PageRank with our data. So I think I have here, this is the TigerGraph GSQL graph algorithm library on GitHub. So github.com/TigerGraph and then GSQL graph algorithms. So if I go in the algorithm folder, now you might want to go, if you're running directly on a server and particularly using the command line, you can use this install script to install the entire library. I'm just going to be picking out individual algorithms. So I'm going to go into the examples and centrality, and I'm going to start with closeness centrality. So it's about 60 lines of code, and it's actually split into a subquery and a main query. And I've actually, so what we're going to do is we're going to copy this. And I can go over here. I'm just going to call it CC. So I click the plus to create a new algorithm, excuse me, a new query. So it gave me this template where it's called CC for my graph, and then there you need to fill in your body. I'm going to just replace this entire thing with my code. Now I've got all these warning lines, and the reason why is the name doesn't match. So let's fix the name. And also the name of the graph doesn't match. The example was called social, but I want it to be called my graph. Okay, that fixed the majority of problems. So I need to change the name and change the graph name there. Now, this was also written for a different graph. It has one source vertex. What you generally need to look at is it traversing the right, is it using the right type of edges, and is it traversing, using the right type of vertices and edges. So I'm gonna change this to flight 2. Oh, I forgot. This is actually the subquery. I already have the subquery here. In Graph Studio, it doesn't like it when you bundle those two, both the subquery and the main query in the same file. So I'm separating them. So this is going to be just my main query. Sorry, I forgot about that. So this is just my main query. I already have the subquery, so I'm not going to do that for you here. But the changes I make, rather than starting at any vertex, I'm going to start at airports. And I'm going to change, is there anything else I need to change here? There's the edge type, flight 2. Oh, there's one thing I saw here. The maximum number of hops is hard-coded in here. I would prefer it to be a parameter. So I'm just going to put max hops here, comment that line out. And I think that is good. Save and install. This will take about, it says a minute. I haven't timed it, but I think it's more like 20 seconds. And we'll run this and see if we get the answer we want. So notice my input parameters. Display is if you want to see the results visually. I think for our size graph, that's really not a good option. It's good when you have like 100 or maybe 1,000, but when we have 8,000 airports, it's not practical. So output limit, that's like number of different airports in the output and the maximum number of hops. Now, this is really for controlling the execution time. And if you don't put in, well, you do have to put in a number, but if you put in a very high number, it'll work. There's actually a built-in limit for the number of iterations, but it's useful in our case because there's a limit to flight itineraries. We're looking at how many hops do I have to get if I want to go from any city to any other city. What's the maximum number of hops I'm going to need to take? And there's no way I'm going to even consider more than making 10 connections. Now, what happened? The query didn't finish because it exceeded the query timeout threshold. So I'll tell you, I am using the smallest type of server that Tiger Graph Cloud offers. We do have heftier ones, and if I had had a heftier one, it would have run faster. The other thing is I could have extended this time limit. I think we'll post a blog afterwards to show you how you can extend this time limit. There isn't a built-in button here, so it is a little bit harder. So I don't want to slow things down. There's another way around this issue by changing what we're going to do. What we're going to do is we're only going to consider flights within the US. And so I'm going to make country a parameter. And rather than starting at just any airport, I'm going to let the user specify. You can narrow down the graph. So where v.country equals country. So that's my input parameter. So the first line says, okay, start with any airport. Now this says, well, hold on, we're going to do a selection. So from any airport, only take the ones where its country is equal to this input parameter country, and then save that as an updated version of start. And so what if somebody does want to do the whole graph, if they leave that blank? So what I'll do is I'll put an if condition. So if country isn't blank, then do this update. So that narrows down the search. Let's save that and install that. And I think we'll find there's probably going to be one or two more useful additions we're going to want to make. But I think to motivate them, we need to see the output. Okay, so now show me 100 airports, maximum 10 hops, and we'll do this for the United States. Okay. TJK, BFI. I'm wondering, okay, there's LAX. There's something that I recognize, that's Los Angeles, JFK. So it did sort the results. That's good. It is showing me the top results, but I don't recognize any of those names. Now, let's make one more change. Right now, the output is determined by, it says print top scores. And what is a top score? A top score is this heap. So we're sorting them according to the score. That's good. But it's a heap of vertex score tuples. And what is a vertex score? So it's got the vertex ID and its score. Well, I would also like a name. And when we construct a vertex score entity, all I need to do is add the name. And I'm getting some, oh, string, not sting. There. And I'm trying to think how I'm gonna, I think since you've seen how I made some of these changes, I'm gonna, after I do this one, I'm gonna go to Betweenness Centrality and PageRank, because I want to talk about looking at the results a bit. Because I really want you to see the difference in results you get with Closeness Centrality versus Betweenness Centrality, and then even PageRank. So the output limit here, just show you, that's not really much of a limit. I'll make it 1,000 just for fun. Now I see this is Talk Junction Airport, Boeing Field, King County. Okay, so I believe that's near Seattle by the Boeing facility. Unalaska, Orcas Island, Friday Harbor. These all sound like Washington State or Alaska, which is interesting. And finally, I think this is the 10th entity. You get LA, then JFK, then Chicago O'Hare, Newark, Houston, Washington, Dallas. So then we're getting results that make sense. Now, so you might want to investigate, well, why did the first 9 results, these small airports in that area? So just remember the question we're asking. To to or from any airport, which one has the shortest overall distance? And I believe we loaded only directed edges. So that means it's possible that maybe in our data set, either there was only one way to get to or from these airports, or it's just such that if you remember, we consider all destinations equally. All destinations are equally important. So you might get some strange results because this does not take into account which one sort of people vote for with the amount of travel, like how many people want to go to these different places. We didn't take that into consideration. We considered every destination equally important. So there's some interesting reason why these smaller airports showed up in the top, but once you get past them, then you get to sort of the expected results. So let's look at Betweenness Centrality now. So I made a couple of the similar changes here. I also added a country filter, and I also added an item for the maximum number of items, so that this wasn't essential, but rather than printing out every airport, you might want to limit the airports. So the changes I made, by the way, were really to add this section. I did the exact same thing here with filtering by country beforehand, and I did a little bit of post-processing to sort the results. The standard algorithm in the library does not sort the results, and we really want to see the best answers first. So put maximum 10 hops, 1,000 output. Oh, I should do a couple other countries also, but I'll do United States first. Whoa. So for some reason, Anchorage Airport is first. But then, okay, Chicago O'Hare is second, LA, Seattle, Denver, Atlanta, Dallas. So we are seeing airports, oh, Bethel. I don't know what Bethel is. Minneapolis, St. Paul. So for the most part, the results seem to make sense. But it's also not identical to closeness centrality. And let's wrap up by, oh, let me do some more countries. Let's do Germany. So Frankfurt is first, Munich second, Berlin Tegel third. Probably makes sense. Japan. Tokyo Haneda comes ahead of Narita International. Interesting. I think if you run centrality, these two are flipped. So this means like, which airport are you most likely to connect through? Not which one does a random traveler end up at most often, but which one is most likely to be a connecting airport if you're doing just domestic travel. And so, as expected for China, Beijing is first, Guangzhou in the south is second, Shanghai is third. PageRank, let's wrap up with PageRank, and then I'm happy to answer your questions. So again, I added a filter for country. That might be the only change I made here. We do need to put in values for everything here. So, and this requires, excuse me, some familiarity with the PageRank algorithm. What are typical values? So this is really limiting. This is PageRank is a convergence algorithm. There's no hard stop to it. You just, after a while, the answers stop changing. So this is saying stop when the change from one iteration to another is no more than this limit. We'll set the maximum number of iterations a little higher. Damping factor, that's sort of a standard value, but it's not a requirement. You can change that. Be happy to discuss the significance of that value. Oops, is it running? Oh, it's finished. So Denver, #1, Atlanta, Chicago. Again, I didn't change it to show the names of the airports, just their IATA scores. So Denver, Atlanta, Chicago, Dallas, Fort Worth, Minneapolis, St. Paul. Pretty reasonable answers, but I realized each of these got slightly different answers. So each of them has a different interpretation, and also had to make some tweaks, some for scalability, some to make the output more attuned to what I want. But there are other things you might want to do. Like, I didn't talk about weighted edges. Weighted edges might be really important in some of your cases. So if you want to consider how much traffic is on this route, I think actually we did look at they were actually considering the distance. So if you look at weighted edges, you're thinking about how many miles are you traveling. If you do unweighted edges, it's just how many connections. For betweenness, what we were looking at again, when traveling from any city to any other city, which airport is most likely to be a connection city? Is that a reasonable question? Do you actually want to consider any city to any other city? You probably have some subset you're interested in. And then PageRank is the random flyer model. If you're equally likely to fly to any route, which airport would be your destination most often? That's probably not a realistic question. Nobody actually travels that way. And here I summarized some of the edits I made. But just to summarize, so centrality algorithms, really you're abstracting the concept of location and travel. So when we say centrality, if you can see some analogy where you're talking about traversal across the edges and you want to see which one is most central with respect to that travel, then look at centrality algorithms. We talked about closeness and betweenness, and they both leverage shortest paths. So shortest path becomes sort of a subcomponent of them. PageRank uses directed referral edges to find the most influential nodes, and personalized PageRank gives you a localized result. And it's actually pretty easy and to modify GSQL library algorithms. I did it in front of you. And it's using syntax that if you know SQL, if you know kind of common procedural programming, it should be something that you could pick up very easily. So again, if you have questions now, we'd be happy to answer them for you. David, have you seen any questions come in? Sorry, I can't. Are you there, David? I don't hear anything. Okay, so these algorithms are actually, we're in the process of publishing the Betweenness Centrality algorithm. So we'll have that up shortly. It is on GitHub. It's in one of our draft draft branches rather than in the master branch on GitHub. I mentioned there are other algorithms available. So if there's any particular algorithm that you're interested in having, send us a message and we will try to see if we can get that one installed.
Victor, it's
yes.
David. I'm back. I had a Wi-Fi issue.
Okay.
Did we go through the Q&A?
I didn't. So I didn't see any more that haven't already been answered. I was wondering if you've seen any. So I mentioned that
one question we have here is, which books do you recommend for algorithms?
Oh, so for graph algorithms in particular, you know, the web is actually a pretty good resource. I didn't have a, when I was in school, I didn't have a book dedicated to graph algorithms. I had one for algorithms in general, which I actually did quite, sorry, which was, I'm looking at, I turned around to look at my bookshelf. Let me see if I can quickly grab that off my shelf. Oh. So this is a comprehensive book on algorithms, which has one section on graph algorithms by Corman and Leiserson. The first author is Corman. There are 3 other authors. There are a couple other. So the question is, if you want to know how they actually work, if you want to study the algorithm the way a computer scientist would, or if you just want a more practical knowledge of what will this do for me and just give me a general idea of the pros and cons of each particular one. So we are trying to, in our documentation, we're trying to give you those pros and cons information, basically what does this do, what to look out for, which graphs does it qualify for, which graphs does it not qualify for, directed versus undirected, weighted versus unweighted, things like that. But if you really want to study how they work, like do a derivation, then that you have to dig a little deeper. And we generally don't do that in our online documentation. In some cases we have a link to the research paper that we refer to. Because one thing about our algorithms, we recently made an update to our shortest path, believe it or not. And the reason why is that because GSQL works on this parallel processing paradigm. And some of the algorithms that are out there, what are considered the, quote, best algorithms, they are in fact best if what you're doing is sequential execution, if you do every step one at a time. But if you're doing parallel execution, then the way that you judge best changes. And there's sort of a separate set of research, more modern research in general, about which are the best parallel processing algorithms. So I think what we'll do is we'll make sure that in our documentation for each of our algorithms, we post a link to the research paper that we used. So which algorithm are we implementing?
Sounds good. Hey, I dropped off, so I don't know if you had a chance to answer that question about are you planning to add the other centrality algorithms that you mentioned?
I said I think Betweenness will be published very shortly. It's ready. Somebody didn't pull the trigger on GitHub, and we probably at this point it's if there's a request. So if you have a request, send it to us. We may actually have it in development already, or we could do it for you very easily.
Sounds good. Perhaps we want to wrap things up, just given the time.
Yep. So
yep. So why don't I take this, go through this slide. So if anyone has additional questions or would like more information or would like to have more personalized engagement, there's at least 2 different ways to do that. One is to join our developer forum at the URL shown at the top there. And additionally, every Thursday at 11 a.m. Pacific, we have what we call developer office hours, when we have at least one of our subject matter experts standing by to answer questions in real time. And if you want to set up or join that session, you can register for office hours at the URL shown there. Additional resources which are available for you to learn more. There are several listed here. Victor was using TigerGraph Cloud, which is a very easy way and also free way to get started with TigerGraph. It just takes a few minutes to get to sign up, about 5 or 6 minutes. And we have multiple, at least 16 starter kits pre-populated starter kits on a range of use cases within TigerGraph Cloud to aid, to accelerate the process for you to start deriving value from TigerGraph Cloud. And so we recommend you to click on that URL there or go to the website and register and create an account and begin using TigerGraph Cloud. I think you'll find it very useful. We also have the ability, we give you the ability to test drive TigerGraph through some online demos shown at the URL there. You can also download the developer edition, and many of the scripts that we use in our Graph Gurus webinars can be accessed at that GitHub location shown there. Next. These webinars are called Graph Gurus. We are bringing these on the road. We call these in-person events. Graph Gurus comes to you. We did one this morning in Munich and another in Houston. We have upcoming events in Seattle, San Francisco, Atlanta, and several other places. But if you are not, if you don't want to wait for us to cycle through to your city, you can reach out to us and we'll be happy to set something up. We do these online events, these webinars every Wednesday. Our next one is episode 28, and the title is an in-database machine learning solution for real-time recommendations, next Wednesday at 11 a.m. Pacific. And then part 3 of this webinar series on graph algorithms that Victor is proposing, or presenting, I should say, will be on February 19th. So part 3 on February 19th. I think you'll all agree with me that today's webinar was phenomenal. I learned a lot. So I'm sure you don't want to miss that one. Again, part 3 in this series of 5 will be on February 19th, and that will be Graph Gurus 29, and the topic will be community algorithms. And additionally, if anybody in the audience today has a specific topic that they'd like us to cover, please don't hesitate to reach out to us, and we'll be very happy to pull together a webinar on that topic. And with that, I'd like to thank everyone for attending. Victor did a fantastic job. I dropped off for a short while because of technical issues with Wi-Fi, but I heard the vast majority of his presentation, and I learned a lot. Hopefully everybody in the audience also learned a lot. We know you had many different ways you could have spent the last 63 or 64 minutes, actually 68 minutes, and we very much appreciate you spending the time with us today. Hope you found it productive and insightful, and we look forward to seeing you next Wednesday on